Today, we're going to journey into the fiery heart of our planet to get our heads around one of its most awesome forces, volcanism. And this isn't just a story about destruction. It's really the story of how our world is constantly being born.
I mean, just look at that incredible power. It's easy to see it as purely destructive, right? But here's the puzzle. How can a force that can literally tear the land apart also be the very same force that creates new islands, makes soil fertile, and sculpts these breathtaking landscapes? That's the big question we're diving into.
To even begin to understand that, our story has to start deep, deep inside the Earth. We've got to find the source of all this incredible energy. So it all kicks off with this really powerful chain reaction. Think of the Earth's core as a giant furnace. It's so hot, it gets the mantle, that huge layer of molten rock just beneath us, churning in these massive currents. It's kind of like a giant pot of thick soup boiling on the stove. And these currents are so powerful, they actually drag our tectonic plates around. So wherever those plates crash into each other or pull apart, the pressure starts to build and build and build. That right there is the engine of an eruption, just waiting to go off.
Okay, so the stage is set. The pressure is on. Now let's follow the star of our show, molten rock, as it starts its dramatic journey up to the surface.
First up, a quick but super important clarification. When this hot, molten rock is still trapped deep inside the Earth, we call it magma. But the second it breaks through to the surface and starts flowing, boom, it becomes lava. It's the exact same stuff, it's just changed its address. A simple difference, but it's totally key to understanding what happens next.
So why is it that some volcanoes have these beautiful, gentle rivers of lava, while others just explode with terrifying violence? Well, the secret is all in the personality of the lava itself, and there are really two main types we need to know about.
On one hand, you have shield lava. This stuff is incredibly hot and super runny, really fluid. And because it flows so easily, gases can escape without any trouble. It's kind of like opening a bottle of soda that hasn't been shaken. No drama. The result is a nice, quiet eruption, with lava spreading out over huge distances. This is exactly how those massive, gentle-sloped shield volcanoes in Hawaii were built. And then you have its complete opposite, composite lava. This lava is cooler and it's thick and sticky. Think of cold honey. Because it's so goopy, it plugs up the volcano's plumbing. Gases get trapped inside and the pressure builds up to insane levels. It's like shaking that soda bottle for a minute and then opening it. All that pressure has to go somewhere, and it goes up in a massive, violent explosion that creates those classic, steep-sided volcanoes we all imagine. And here's where it all connects. The biggest difference between them? A single ingredient, silica. You can think of silica as the thickener in the recipe. Low silica gives you runny, easygoing lava that builds shield volcanoes. High silica gives you thick, sticky, gas-trapping lava that leads to explosive, steep, composite volcanoes. That one thing dictates everything. It's a perfect, real-world example of cause and effect.
So whether it's a quiet ooze or a violent blast, when all that rock finally cools down, it leaves a permanent mark. Let's dig into how these eruptions act as sculptors, shaping the very ground we walk on, both on the surface and deep below.
Geologists basically sort these volcanic landforms into two big families. Extrusive forms are the ones we see on the outside. They're created when lava cools down on the surface. Intrusive forms, well, they're the hidden architecture. They're made when magma cools and hardens underground before it ever sees the light of day.
The extrusive forms are like the celebrities of the volcano world. You know these. We're talking about the gentle giants like Mauna Loa in Hawaii, the picture-perfect cones like Mount Fuji in Japan, and even these mind-bogglingly huge lava plateaus that can cover an entire region. These are the structures that we see and that define these volcanic landscapes.
But then there's the hidden world. When magma doesn't quite make it out, it cools into these really fascinating shapes underground. It can squeeze into vertical cracks to form something called a dike, or spread out horizontally between rock layers to form a sill, and sometimes it creates a massive, deep chunk of granite called a batholith. This is literally the hidden plumbing of a volcano that we only ever get to see after millions of years of erosion have worn away everything on top of it.
Okay, so we've seen how volcanoes get built, but how do we describe how they behave? Let's zoom out and classify them not just by their shape, but by their personality and their current mood, so to speak.
Eruptions really exist on a scale of intensity. At the calmest end, you've got the gentle lava fountains of the Hawaiian eruption. As you move up the scale, things get more and more violent, throwing ash and gas higher and higher into the sky, and at the most extreme end,
you have the Plinian eruption. This is the big one. We're talking a catastrophically violent event with incredible power. In fact, it's named after the eruption that famously buried the city of Pompeii.
And finally, we classify volcanoes by their life cycle. Active volcanoes are the ones erupting pretty regularly, like Mauna Loa. Then you have dormant volcanoes. You can think of them as sleeping. They're still alive and could wake up at any time, like Krakatoa, but they've been quiet for a while. And then you have extinct volcanoes, like Mount Popa. For them, the show is over. They're considered geologically dead, with no chance of ever erupting again.
So, from the very core of our planet to its highest peaks, volcanism is this constant, dynamic force. It's a powerful reminder that the ground we stand on isn't static. It's being remade all the time. It really proves our planet is truly alive. And for all of us, the question isn't if the next great eruption will happen. It's just a matter of when.